let's talk about a really fascinating phenomenon called total internal reflection. All right. Now, suppose I have light going from a denser to a rarer medium. So for example, water to air. Okay, just imagine that I have a little laser pointer and I'm pointing it, I have it underwater and I'm pointing it at the surface. So the laser light comes out like this and it hits the interface. And let's say that, okay, I'll just make this angle a little steeper. So the light comes in like this from my laser or a flashlight, and it undergoes refraction. Will it bend towards the normal or away from the normal? We just did this.
Away from the normal.
Away from the normal, because it's going from a larger end to a smaller end. So it will do something like this. All right. Now suppose I increase the angle of incidence. So this is my angle of incidence. Let's call it θ1. And this is the angle of refraction. Let's call it θ2. Let's increase the angle of incidence a little bit. So let's make the angle of incidence something like this. So as I keep on increasing the angle of incidence, the angle of refraction will also keep on increasing, right? And so if I keep on increasing the angle of incidence, there will soon be a certain angle, or let's say I've slightly increased the angle of incidence. So now θ1 is larger and θ2 has increased. So it's even closer. It's like that, right? Now, if I keep on increasing the angle of incidence, soon the angle of refraction will be 90 degrees and it'll look like this. So for a certain angle of incidence, theta, the angle of refraction can be 90 degrees, which means that the refracted ray is just grazing the surface. That makes sense? That particular angle of incidence in the optically denser medium is called the critical angle. So theta critical is the angle of incidence in the denser medium. Angle of incidence in the optically denser medium. When I say denser, I really mean optically denser, meaning large N, denser medium, where such that the angle of refraction, I'll just call this theta r, is equal to 90 degrees. So I'll just call these theta I and these as theta r. That's probably a little better. Such that the angle of refraction is 90 degrees. That makes sense? Or the refracted ray is just grazing the surface. That clear to all of you? Okay, so that is called the critical angle, right? We can actually calculate the critical angle quite easily by applying Snell's law. So let's say that this is N1 and this is N2, right? Or let's just to be clear, let's call this N air and this is N water. And let's call this N air. So it's easy to remember what is what. So let's apply Snell's law in this particular case. N water sine theta c is equal to N air sine 90. That makes sense? So you can see from here immediately that theta c sine 90 is 1. So theta c is sine inverse of N air divided by N water. That makes sense? Which is sine inverse of N air is approximately 1, N water is 1.33. And so if you do that, I think it's going to be something like 48 degrees, if I remember correctly. That makes sense? So that means the critical angle is 48 degrees for an air-water interface. You can clearly see that the critical angle depends on the pair of media concerned, right? So the critical angle is greater than, the critical angle is 48 degrees for air-water interface. That clear to all of you? So if you shine the ray at an angle greater than 48 degrees, if I remember correctly, let me make sure that it's For water to air, it's about 50 degrees, not 48 degrees, sorry. So if the angle of incidence is greater than 50 degrees, then is less than 50 degrees, you'll have refraction. And if it's equal to 50 degrees, you will have refraction, but the refracted ray will be grazing the surface, right? Now, here comes the really fascinating thing. What if you make the angle of incidence greater than the critical angle? So let's see what happens then. So this is the angle, this is the air-water interface, this is the normal, and this is theta c. Now we are shining the light at an angle greater than theta c. So theta is now greater than theta c, right? So what's going to happen in that case? A truly amazing thing happens. The light will be reflected back into the medium. That is absolutely amazing because water and air are both transparent, right? So how can the light be reflected back? But it is reflected back. And not only that, this reflection is perfect, absolutely perfect. Normally, when you have a mirror, suppose you have a mirror here, and this is the symbol for a mirror as we'll see in the next chapter, and you shine some light onto the mirror and the light reflects, there is always a little bit of absorption by the mirror. So the intensity of the reflected light is a little bit less than the intensity of the incident light because the mirror will eat up some light. But when you have this kind of reflection, it's absolutely perfect. All the light, 100% is reflected, right? So this is called total reflection. And technically it's called total internal reflection. The word total comes from the fact that there is absolutely no absorption of light in the process of reflection, which is almost always the case when you reflect off of some material. So this is total internal reflection, and it happens when the angle of incidence in the denser medium is greater than the critical angle for the pair of media concerned. That clear to all of you? So I'll just correct this. This is 50 degrees. That makes sense to all of you? So this is total internal reflection.